All right. Yesterday we ended class by essentially making the statement that if if a wave has a long wavelength, I want to do it this way, has a long wavelength, and a long wavelength, low frequency, it would tend to have low energy. And then we said that if a wave has a short wavelength and high frequency, it would tend to have high energy. So that's basically the opposite. We also were introduced to some symbols to represent these things. So wavelength is the upside down Y, also known as the Greek letter lambda. Frequency is this fun little V. I'll draw that a little bit better.
Your screen's frozen.
My screen is frozen. Sorry. So frequency is this fun little V, and also known as the Greek letter nu. And then energy is really difficult. Energy is just a large capital E. That's how we represent those things. Okay, so those are sort of the things that we talked a little bit about yesterday. And as a result of that, we are now going to move into something more specific about the electromagnetic spectrum. And in your note packets, there is the electromagnetic spectrum diagram that is like all gray and white. And on my end, you're going to see that it has some colors to it. But we're going to talk about that in a second. Okay. Now, this electromagnetic spectrum, sometimes it's referred to as the EMR spectrum, electromagnetic radiation spectrum. Okay. Sometimes it's referred to as EMR. But what really you need to be able to see here or identify is what this image shows you. There's a lot of information on this image. Okay. And so I'm going to try to go through that a little bit. Now, one thing I'd like to point out is on the top of the image is wavelength measured in nanometers. Okay. And to kind of focus on the wavelength a little bit, remember that wavelength is the symbol, the upside down Y symbol. Okay. On one end, in this case, I'm going to focus on the right side first. You see that there is a 10 raised to the 12th power. What that really means is it means 1 times 10 to the 12th, okay, which actually means that. So it's really 1 with like 12 zeros after it, nanometers. And what I really want to try to illustrate here is that's really quite large, okay? On the left side of this particular equation, or diagram, you see 10 to the minus 2, and so that means 1.0 times 10 to the minus 2, which actually looks like this. And in terms of distance or length, that's actually very, very short. Okay, so on one end, we have long wavelengths. And on the other hand, we have short wavelengths. Okay. On the bottom of this diagram is frequency. And frequency, we said yesterday, had a unit of the per second. So sometimes it's written like this, 1 over second, or second minus 1. Okay. Now, on the right-hand side, we have 10 to the 4th. which is really, in reality, it is 1 times 10 to the fourth, which is actually like 10,000. Okay. So on the other side, we have 10 to the 20, which is actually 1 times 10 to the 20, which is going to be like 1 with essentially 20 zeros after it. So it'll be like something like this. Something like that. And that's your frequency. So on the left-hand side, where you see 1 times 10 to the 20, that's actually really, really high frequency. So we have really high frequency over here.
Dang, that's a big number.
And on the right-hand side, you have low frequency. Like that. Now, how this relates or correlates to energy is the side of the diagram that has long wavelengths and low frequency has low energy. And the side of the diagram that has short wavelengths and high frequency has high energy. Now, hopefully what you can identify or at least figure out here is you might be familiar with some of these different types of electromagnetic radiation. On the low energy side, we have things called radio frequency, which is basically radio waves. Okay. And then next to that, moving one step to the left, are microwaves. And then next to that, one step to the left, are infrared waves. And then we have something called the visible light spectrum, which has actually kind of been pulled out for you to take a look at in terms of the colors. And then next to that, to the left, you have the ultraviolet. Then you have X-ray, and then finally you have the highest energy, which is gamma rays. Okay. Now, radio waves are the wavelengths are so big and they have such low frequency that they are incredibly harmless for the most part. Like you are constantly being bombarded by radio waves all the time. Microwaves have a bit more energy, which is why we use them to cook our food with. Infrared, if you have a true infrared lamp, it produces a lot of heat. So sometimes years ago, they used to like put food under a red light bulb, and that was an infrared light bulb to keep it warm. Ultraviolet is usually associated with black lights, and then X-rays, we know what those do, and then gamma rays are incredibly high energy. Okay.
Isn't infrared, or which is the one that like when we look at our like phones and stuff?
It's a blue light.
I thought it relates some sort of like radiation.
There is some radiation, but most of the radiation given off by your phone is super low energy, and it doesn't really have that much of an effect, or studies have shown that doesn't have an effect. Yes?
Oh, so my parents told me it's bad to stand in front of the microwave.
Yes. So your parents told you it's bad to stand in front of the microwave. The reason why your parents and older adults feel that way is because when microwaves were first put into the consumer market, the general belief was that the microwave radiation, the energy that was coming out of the microwave that was cooking your food, would be strong enough to also cook you if you were standing next to it, because like the window, like the idea was that the microwaves would go out the window and get you. The reality of that is it's really not the case. It's not exactly how microwaves work. In reality, there is a box, like if you look inside your microwave where the panel is, where you pump in all the numbers, usually to the, like on that side, there's a microwave generator in there, and that microwave generator is designed to like emit microwaves at a certain frequency, and the microwaves are designed to like contain that. So when the microwave beeps, that 1, 2, 3 beeps, in theory, what's supposed to be happening there is the microwaves are supposed to have dissipated during that 1, 2, 3 beep time. So as long as you wait, you wouldn't be like bombarded with microwaves. However, when microwaves were first a thing, everybody thought that you would get microwaved. Okay. And also be aware that microwaves were like $1,000 when they first came out in the market. Now you can go to like Meijer or Target and buy one for like $75. Well, they made tons of them, but it was just new technology. It's like when they come out with new phone or like 4G TV or whatever.
4K.
4K, that's the word. I don't know. My TV is so far behind. I don't even know what it's. My TV is probably like -K. So there's that. Now, next thing. You have to be able to know how to read that diagram and answer questions about it for an assessment going forward. So we're going to practice that right now. Okay. The first question says, which type of electromagnetic radiation, EMR, has the shortest wavelength, right? So if I go back up to my diagram and I look for the short wavelength side, what I'm looking for is the side where the wavelength, which is the numbers up on top, are really, really tiny. So 1 times 10 to the minus 2 are really tiny. So that tells me I would probably be talking about gamma rays. Which type of electromagnetic radiation has the longest wavelength? That would probably be the opposite. So in this case, going back up to my diagram, I see long wavelengths are somewhere in between 1 times 10 to the 12th. So these would probably be radio frequency waves. So radio electromagnetic radiation. And then what type of electromagnetic radiation happens to have the highest frequency? So I'm going to go back up here, and I see that over on the left-hand side, the gamma rays have a frequency of 1 times 10 to the 20, and that's the biggest one on there. So I'm going to say that they would be gamma. And then which ones have the lowest frequency? That would be also on the other side, which would end up being radio waves. I'll show you that in a minute. So up here on the top, 1 times 10 to the 4 is the smallest value up here. So that's going to be my lowest frequency. So that'll be my radio waves. Gamma rays are incredibly not safe for you to be bombarded by. So we try to avoid them. One of the things that makes gamma rays dangerous is that they can have an effect on the DNA and cause a mutation in your DNA. So they're not going to make you become like Spider-Man, but they are going to make you like potentially have some type of like they'll start creating what we call free radicals, and that can be really bad for you as a human. So we try to avoid those. The Japan thing. Oh, the bomb that was dropped produced high energy. And that high energy did cause the fallout from it, did definitely cause like leukemia and things like that. So yeah, there were some things there. Now, the next type of questions you're going to be answering or addressing are questions like this: what type of electromagnetic radiation has a wavelength of 5.4 times 10 to the 6 nanometers? Okay. Now, what's critical here is that the 5.4 actually doesn't matter. What really matters is the times 10 to the something, whatever that exponent is. So if I go back up here and I look for wavelength and I look for something that is 5 or that is times 10 to the 6, I see times 10 to the 6 is right here. Okay? And times 10 to the 6, it doesn't matter. It could be 1 times 10 to the 6. It could be 5 times 10 to the 6. It could be 9 times 10 to the 6. It's still going to fall in that microwave category. And so as a result of that, the answer here would be microwaves. The next one says, what type of electromagnetic radiation has a wavelength of 500 nanometers? So now I'm going to go back up to my diagram, and I actually see that in the visible light spectrum, right, there is 500 nanometers measured here. So you could simply answer visible light, and if you happen to have a color diagram, you could answer green. But the correct answer here is visible light.
Wouldn't it be infrared? 'Cause it's like to this 14, and then you go to the wavelength, and then it's 10 to 14. It's infrared.
Oh, so the question is, wouldn't it be like ultraviolet? Is that what you're saying? Or infrared? Oh.
Yeah. 'Cause it's under.
But it's. I hear you, but like the technically the visible light region is such a tiny band that this is going to be one of the cases where like the times 10 to the 14 kind of spills into the infrared, but the band is super tiny here. Okay, so when we actually talk about that, you would, if I asked you a question about the frequency and I said like 6 times 10 to the 14, that'd be the one time when like the 6 would matter. Okay. So that was your, okay. All right. The next one, we're going to talk about frequency, 5 times 10 to the 18 per seconds. Okay. So again, I'm going to go look up for my electromagnetic radiation. That is a frequency. These are the ones that are on the bottom, and these are times 10 to the 18. And I see times 10 to the 18 is right there. Times 10 to the 18 falls in the X-ray category. So I'm going to fill in X-ray here. What type of electromagnetic radiation has a frequency of 4.5 times 10 to the 13 per seconds? So I'm going to go back up here and look for times 10 to the 13. 10 to the 13. Oh, there isn't a times 10 to the 13, but there's a times 10 to the 12, and there's a times 10 to the 14. So that means that this is probably times 10 to the 13 here, and so that tells me that's going to be infrared. Okay, now, yes?
What is the S-1?
So the unit for frequency is something called the per second, or it's actually called the hertz as well. But the unit is S-1. And so if I go back up to the top here, oh, I didn't do it on this. Oh, yeah, I did. So right here, that's what that means, is per second. Okay? S-1, second -1, that they're the same thing.
So it's how many wavelengths per second?
Yes.
Okay.
Now, we're going to jump into something called the photoelectric effect simulation. And so I do have a simulator for you that I'm going to go through. And what I need you to do is locate the slide in your notes that looks like this, the photoelectric effect, this part right here. Yes? Okay? And then we're going to kind of do this one together. So here is the photoelectric effect simulator. And what I would like to tell you is that the photoelectric effect simulator is a device, rather, that has the ability to measure current. And what happens is that there is a metal over on the one side, and then on the other side there's a detector, and that detector is detecting whether or not electrons are being transferred from the metal to the other side where the detector is. So there's lots of metals a person could choose from. We're going to use sodium in this instance. So this pad right here is coated with sodium, basically. And if I turn off the flashlight, there's just like this little thin band of metal right here. That's the sodium. Okay. Now, I'm going to turn on the flashlight. And this is a very special flashlight. It has the ability to transmit very specific frequencies or wavelengths of light. So right now, it's transmitting infrared light, and nothing is happening. Okay, but if I take it and I set it to go to like 700 nanometers, so on your table, you would want to write 700 nanometers. Okay, so you would have red would be the color of the light that you would have, and I know you can't see this, but you can do it. 700 nanometers. So on your table, you'd have red and 700 nanometers. And the observation that you're going to make here is that actually nothing is happening. There's no particle movement. So I would write where it says amount and speed of electrons, I would write no particle movement. Pardon? No, it's not. There's actually nothing happening here. And I'm not flipping back and forth. You're filling this in as we do this. What? Now, if I change the wavelength to, let's see, 500, if I change the wavelength to 500, we see particle movement. Okay? So there are some particles moving. They're not going super fast. So what I would write in my notes is the color of light would be green. The wavelength would be like 500 nanometers. And I would say that there is some particle movement at a slow rate. Okay. So there's some particle movement at a slow rate. Now, the next thing that we're going to do is we are going to change the light to violet, and I'm going to crank it down to, or I'm going to set it at like 400 nanometers.
So blurred.
Well, they're moving faster, and also my projector isn't super high quality anymore. It was top of the line once upon a time, but that was about 7 years ago. And the bulb in there is probably old, so like, you know.
Oh, does it look good before?
Yeah. I don't know. Anyway, so I would say that we are now at violet. And we set the wavelength to 400. I would say there is more particle movement. And I would say that that particle movement is occurring at a faster rate. And then the last one that we're going to do is I'm going to set the wavelength to ultraviolet, and it's got even more fuzzy. I don't know what happened there, but I can tell you that the wavelength is 100 nanometers. So we are at ultraviolet. The wavelength is 100 nanometers, and this is even more particle movement. At an even faster rate. So there's a lot of things going on there. So what I'm going to do is I'm going to come back to my notes for those of you that might have missed something potentially. So we did, the first color that we did was red. The wavelength was 700, and there were no particles moving. The next thing we did was green. The wavelength was 500, and there was some particle movement, and they were going kind of slow. The next thing was violet at 400 wavelength, and there was more particles moving, and they were at a faster rate. And lastly, the ultraviolet at a very, very tiny wavelength, and the particles were moving at a really fast rate. So what we're really trying to get at here is the idea of something that's referred to as the photoelectric effect. The photoelectric effect has been an observable property that happens when you shine light of a very specific wavelength and frequency on metal. When you shine light on metal of a very specific wavelength and frequency, electrons actually get ejected from the metal, and we can observe that. Okay, but in order for that to happen, one of the things that didn't make sense was that if in order to move a particle, you generally have to have another particle make that happen. And since energy or light we knew that behaved like a wave, there was really no reason why this should have happened. So what was theorized and eventually found out to be true is that light not only behaves as a wave, but it also behaves as a particle. And when it behaves as a particle, it's called a photon. Okay? A photon is essentially this packet of energy that has a very, very specific value, and it's basically this massless particle that is being emitted or transmitted in the form of light. So light behaves like a wave and it behaves like a particle at exactly the same time, all of the time, and it's very, very difficult to wrap our heads around it because it's an incredibly difficult concept. The best way for me to potentially try to illustrate this is, how in gym class there's that one kid who's kind of not so bright, and they kick a medicine ball in the weight room. You know what I'm talking about?
And hit the fire.
Well, no, not hitting the fire alarm, but I'm talking about the kid that kicks a medicine ball. You ever try to kick a medicine ball?
Yeah.
It breaks your toe. Well, not quite, but it doesn't feel good, right? So when you kick a medicine ball, the medicine ball doesn't go anywhere. Okay, because you have low energy because look at you, it's 7th hour and you're done for the day, right? But when I kick a medicine ball, it goes halfway across the room because I've got more energy, right? But when Giannis kicks a medicine ball, it basically punts from here to Greece. You know what I'm talking about? Because he's got super high energy. Wouldn't it be cool to be like Giannis's friend?
That'd be amazing. That'd be.
Not even talking about he just seems like a cool guy to hang out with. He says funny stuff all the time. He always seems to be happy. He does like himself an Oreo. You know what I'm saying? Anyway,
He likes Chick-fil-A and Culver's.
he does like Chick-fil-A and Culver's. He just seems like a fun guy to hang out with. Anyway, coming back to this. So the reason why I bring up the kicking of the medicine ball and people with more energy kicking the medicine ball and getting it to go faster is that's exactly how the photoelectric effect works. So down here in this picture, right, the one on the left-hand side, those waves look like bacon, but they're not. They're simply red photons. Okay. Now, these particular red photons have a long wavelength. Okay. They have a low frequency and they have low energy. Okay. And I guess to review, we would say wavelength is the upside down y, known as lambda. Frequency is the fun little v, also known as nu. And energy is just an E, because why not? Now, in the middle diagram, you have green bacon, and if you have green bacon, you probably shouldn't eat it, but really it's green photons. And here you have medium wavelength. You have medium frequency, and you have medium energy. Okay. Now, what I want to note here, and on your diagram, okay, you don't see these red or these yellow circles. Do you see those? You see those yellow circles up there? On your note packet, the yellow circles didn't copy well. So on the red photon chunk of metal, there are no yellow circles. These yellow circles are electrons. So in the red photon part of the diagram, there are no electrons being emitted. Okay. In the green photon part of the diagram, there are electrons being emitted, but they're not being emitted that far. And so now we have the purple photons, and if you have purple bacon, that sounds like it's going to be a really bad day. Because at that point, you're ingesting some type of fungus probably. Okay, but in reality here we have short wavelength, we have high frequency, and we have high energy. So in this instance, note that the electrons are further away from the metal than the green photons, and then the lack of electrons on the metal. So again, going back to my medicine ball analogy, the red photons would be you kicking a medicine ball, doesn't go anywhere. The green photons would be me kicking a medicine ball, they go like halfway across the room. And then the purple photons would be like Giannis taking care of business, putting up 40 points and 12 rebounds last night. I mean, he just decided to like, do my thing, be humble about it. So what does this tell us? Okay. We know that light behaves as photons and light can behave as a particle, right? Okay. So if a photon with enough energy gets absorbed by a chunk of metal, it will kick an electron out. When it kicks an electron out, that electron, how far away and how fast it travels from the metal is determined by how high of the energy the photon is. So now we have this duality of matter theory that basically says light is energy, but it's also a particle at the same time, and so it has some type. Light can be matter, even though it's not. So that is a really complicated idea to wrap your head around. And what you need to be able to tell me is that light is made up of photons. So what you need to be able to tell me is that light is made out of photons. Photons are particles. Okay. And then light can behave as a wave also. So light can be both a particle and a wave. You need to be able to tell me that. Now, to, I guess, make a table or categorize the information that we talked about today, when the red photons, so the color of the photons was red, the wavelength was long, the energy was low, and the frequency was low. But the speed at which the photons was traveling was 3.00 times 10 to the 8 meters per second. Okay. Now, with the green photons, the wavelength was, I guess, a medium wavelength. The energy was medium energy, and the frequency was medium frequency. But the rate at which the photon traveled was 3 times 10 to the 8 meters per second. And then when we had the violet or purple photon, we had a short wavelength. We had high energy. We had high frequency. And the photon was traveling at a rate of 3 times 10 to the 8 meters per second. Now, what you need to be able to tell me is that a photon with a specific amount of energy, you need to be able to tell me that the shorter the wavelength, that the shorter the wavelength, the higher the energy. But you also need to be able to tell me that as frequency increases, energy increases. So you need to be able to look at a scenario or look at some data and be able to make heads or tails of what that tells you. What I mean is that if there is a really tiny wavelength, if the waves are really, really tightly packed together, there's more energy. You also need to be able to tell me that if the frequency is really, really high, the energy is going to be really, really high. Okay? So there is the lesson for today. Any questions about the lesson for today? Okay. Your homework is to complete the next worksheet in the packet. It is a one-sider. It's 10 questions. I'm betting that almost every single one of you can finish it before you leave today. Some people asked if I could leave this picture up so you can see the colors while you're answering the questions, and I absolutely will. But get your homework out and let's get it done. Woo!